Welcome to this comprehensive Go programming course for beginners. Throughout this course, you'll learn key concepts and techniques to write performant, idiomatic Go code. You will be guided by the expertise of Lane Wagner and Alan Lyers, who combined have over 18 years of coding experience. Alongside mastering topics such as variables, function, loops, and more, you'll also have the opportunity to apply your newfound skills in 7 real-world projects, ranging from building an RSS aggregator to implementing authentication with API keys. So, get ready to unlock the incredible potential of Go.
Go has been exploding in popularity recently. It feels like all of the most modern tech companies are using Go to build scalable back-end infrastructure. It actually makes a lot of sense. Go is fast, lightweight, has an amazing developer experience, and is actually super easy to learn. Stick around, and in just a few minutes, I'll explain the rest of the reasons why Go could be a game changer for your coding career. At this point, I'll just introduce myself really quickly. I'm Lane, the founder of Boot.dev, and I've been writing Go for a little over 7 years, and I've been building software for about 10. I've actually spent over 2 years designing this Go course, and I've taught thousands of students with this material. The feedback from all of my students over the last couple of years has actually been incorporated in the course, so everything is very battle tested and up to date. I was actually just making some updates yesterday. So how does this course actually work? Well, we're going to start by doing over 100 hands-on coding lessons and exercises. Now, when we're done with all of that, you'll actually have a really strong grasp on the fundamentals. So at that point, we'll go build a production-ready backend server in Go from scratch. Now, I'm begging you, please do not binge watch this video. Tutorial hell is a very real place, and it's a place that you will go if you don't write your own code. Get your hands on the keyboard and write some code with me. In fact, you should actually be coding ahead of me and only using my solutions when you get stuck. So head over to boot.dev and create a free account. That's where all of the code samples for this course are hosted. Now, alternatively, I have linked a GitHub repo in the description below. All of the raw code for the samples in this course are hosted there. It won't be quite as streamlined of an option, but it is an option. Now, you should also know that this course is just one part of the full backend developer career path over on boot.dev. So if you're interested in going from zero to hired as a backend developer, you should definitely check that out too. Now, as long as we're talking about external resources, know that if you get stuck during this course, you have some options for help. First, you've got the boot.dev Discord. Second, you've got the free Code Camp Discord. And third, you've got the free Code Camp forum. I will link all of those down in the description below. Okay, one last thing before we jump into the course. If you want to connect with me personally, or you want access to my other Go and backend content, then you can follow me on Twitter @WagsLane, or you can subscribe to my YouTube channel @boot.dev. I'll link both of those down in the description below. With all of that out of the way, let's talk about Go. Everyone always wants to talk about how fast the Go programming language is. Let's talk about it, and let's compare Go to some of the other more popular programming languages. So in terms of execution speed, Go is much faster than JavaScript, Python, Ruby, and PHP. Pretty much any interpreted language, a language that's not compiled, is going to be slower than Go because Go is a compiled language. Now, don't worry too much if you're not familiar with the terms compiled and interpreted. We'll talk about those in just a minute. For now, just understand that Go is much faster than these languages when it comes to executing programs. If we're doing computationally heavy work, Go is going to be much more performant than some of these other languages. Now, here on the other side, I've listed some compiled languages. So when it comes to compilation speed, Go is actually much faster than these compiled languages when it comes to compiling the code. Now, again, we'll talk about compiling in a minute, but for now, just understand that you have to compile your code before you can run it when you're working with a compiled language. And so by having a fast compilation speed like Go has, it actually increases developer productivity quite a bit. We can iterate more quickly on our code. We can deploy it more quickly. It's not as expensive to run tests, to compile the program and deploy it to production. So this is actually a huge benefit that Go has. Now, I do want to point out that Go does not necessarily run faster. It does not necessarily have a faster execution speed than all of these languages, but it does beat them handily when it comes to compiling. Not to beat a dead horse, but I want to talk a little bit more about execution speed. So we talked about how Go is generally faster than the interpreted languages, right? Python, JavaScript, Ruby, PHP, and so on. It gets a little interesting when we compare Go to kind of the natively compiled languages, or the languages that compile directly to kind of machine code that runs on your CPU, versus the compiled languages that run on top of a virtual machine. Right, so the two big ones that run on a virtual machine are Java and C#, while some of the compiled or natively compiled languages that you'll be familiar with might be Rust, C, C++. Even though Go is a natively compiled language, a language that compiles directly to machine code like Rust, C, and C++, its execution speed is actually more similar to Java and C# when it comes to its runtime speed, how many computations it can do kind of per second. And we'll talk more about this later, but the primary reason for that is the Go runtime. There's basically a chunk of code that's included in every Go program that manages memory, and that tends to slow down the execution speed a little bit. That said, it is worth pointing out that a Go program tends to use much less memory than Java and C# because there isn't a need for an entire virtual machine. Here we are, the first coding challenge. Let me break down what we are supposed to do, and then I'll kind of explain what this code over on the right actually does. So our assignment is to log the string starting Textio server to the console instead of hello world. So throughout this course, we'll be building out little pieces of the Textio product, which if you're familiar with Twilio, it'll kind of be like a Twilio clone. It's a kind of back-end server that sends SMS and email messages and works a lot with kind of textual data. Every file of Go code has a package declaration at the top. Here we have package main simply because this program builds into an executable Go program, right? So we can run this code kind of standalone. The next line is importing the FMT package from the standard library. We're importing it because we're using it down here within the main function. Now, the main function is the entry point to the program. So every Go program starts execution at the top of the main function, which is just a function named main that takes no inputs and doesn't return anything. On line 6 and 7, we have some single line comments. These don't execute. They are not part of the program. They're just there for documentation. And single line comments just start with that double slash. Finally, on line 8, we have the one thing that this program actually does, which is print the string hello world to the console. So let me go ahead and run that. See down here, printed to the console. It's using the standard library's FMT package and the print line function that is exposed from that package to do so. So the assignment here is pretty simple. We're just supposed to swap out that hello world message for starting Textio server. I'm gonna run that and make sure it looks like what I would expect. We're good to go. Next, let's fix a quick bug. I love quick wins. We're not going to talk about all of this syntax in this program. What we're interested in is just fixing the math bug on line 17. So the assignment description says, Textio users are reporting that we are billing them for wildly inaccurate amounts. They're supposed to be billed for $0.02 for each text message they send. Something else is happening. So the total cost here is being set to the cost per message plus the number of messages. Now that doesn't make a lot of sense to me. Go ahead and pause the video, see if you can figure this one out on your own. To me, it looks like the cost per message should be multiplied by the number of messages, right? And let me run it like this so that we can see. Doris spent 4.02 on text messages today. 4 messages. That doesn't make sense, right? For 4 messages, she should not be billed $4.02 if each message only costs 2 cents. So I'm going to go ahead and change that to a multiply. I would expect 8 cents. Yep, Doris spent 8 cents on text messages today. Cool, going to go ahead and submit that. This is one of my favorite XKCD comics. You can pause and read it really quick if you'd like. Slow and resource expensive compilation times are a really terrible thing to work with. I've worked on systems in Java and C++ that took over an hour to compile the code. That means that if we find a bug and we want to deploy it to production, even if we get the bug fixed within 5 minutes, it's still going to take an hour just to build the new production version so that we can deploy it on our servers. I've personally never worked on a Go program that's taken more than just a couple of seconds to build and compile. So the first question is, Go code generally runs blank, then interpreted languages, and compiles blank, then other compiled languages like C and Rust. So the answer is going to be faster and faster, right? It runs faster than most interpreted languages, and it compiles faster than most compiled languages. So the question on this one is, does Go generally execute faster than Rust? The answer is going to be no. So I've thrown around this word compilation or compiled a few times, but we haven't really talked about what it means. When we write code, we write it in a human readable format, right? Typically in a file, in the case of Go, a .go file, right? Maybe main.go. And this file is going to contain human readable text, right? Go code that we as developers work on. The thing is, your computer's hardware doesn't know what any of that human readable text means. Your computer's CPU only understands binary, right? Which is ones and zeros, right? Which at the end of the day is just numbers, right? But it's just numbers and simple operations, things like add and subtract. So we need some process that we can use to convert human readable code to machine code that can be executed by the computer's hardware. And that's all that compilation is. Compilation is just the process of taking some human readable code, right? Go code in our instance, and converting it to binary or machine code that our computer can actually understand. So what does this process actually look like? Well, normally you'd start by writing your Go program. So say main.go. And you'd run it through the Go compiler. On your command line, you'd type go build. And that would produce a new file, which is the executable program. Let's say we were doing a hello world program. It might be hello world.exe, right? An executable program on your computer. And then you could run that executable directly on your operating system without ever having to use the Go toolchain again. So the great thing is you can take this hello world.exe program and give it to someone else, and they can run it on their computer without ever having to install the Go toolchain or even know that you used Go to build the program in the first place. This is different than languages like Python, where if you want to run someone's Python code, you have to use the Python interpreter every single time, and you run the source code directly on your machine. It's also worth pointing out that part of the reason that compiling is so much faster at runtime is that we do all of this compiling work up front. So when we go to run the executable, we don't have to do any conversions from human readable text to binary machine code. That's different than how interpreted languages work. With an interpreted language, as we run the program, the interpreter is reading the human code and kind of at runtime converting it to machine code that the CPU can operate on. So you might be wondering, where's the compiling happening here on bootdev? Well, we actually do the compiling and the running at the same time for you. So when you click the run button, we're actually taking your code, shipping it off to our servers, compiling it, running it, and giving you the result. Don't worry, when we get down the road to the actual project, you'll be building and running your own Go code on your own machine. But we can see the difference between a compiler error and a runtime error, even here on bootdev. So for example, here in this code, the assignment says, to pass this exercise, fix the compiler error in the code. So I'm just gonna run it as is, and you'll see we get this nasty error here, and it says main.go, right, line 6, syntax error. This is actually a compile time error. So we weren't even able to compile this code. It didn't fail at runtime, it failed at compile time, right? Which again, that distinction will become more clear a little bit later. So anyways, we can fix it by adding that close parenthesis that was missing. And now it compiles and runs just fine. So to review, Go code, like this little Go program here that prints hello world, that's not understood directly by the hardware on your computer. Your computer's processor or your computer's CPU understands machine code. So we need to take our human readable Go code, run it through the Go compiler to produce the machine code that we can run directly on our CPU, right? The CPU is designed by the manufacturer to run a specific format of binary. Cool. So the question for this exercise is, do computer processors understand English instructions like open the browser? No. Processors are not ChatGPT. They need machine code. Now, we touched on this very briefly before, but I want to talk about how you distribute a compiled program versus how you would distribute an interpreted program. So let's say that you'd written a script in Python. So you've got this script, main.py, right? This is raw Python code. And you want to give it to your friend so that they can run your script. Well, all you would do with an interpreted language is give your friend the main.py file, and then on their computer, they would run the command python main.py, and they'd be able to run your code. Now, there are a couple of downsides to this approach. The first problem is that your friend needs to have Python installed on their computer. So your friend being able to use your program is dependent on them already having Python installed. It's even dependent on them knowing how to use it or knowing how to use a command line, right? So distributing the programs of interpreted languages can be tricky because it's really only useful if you're distributing to other developers who know how to use these tools already. The other problem is the code itself. Let's say you spent, many weeks writing this Python script and it's super useful and you're trying to sell it to customers. If you just give them your Python code, they effectively own it, they can change it. Even if you didn't intend for it to be open source, congratulations, it's now open source. The problem is you can't really allow someone to use your program without giving them all of the special sauce that makes it work. Let's review how this works in a language like Go. So in Go, we'd start the same way, right? We'd write some human-readable Go code in a file called main.go. But instead of giving that file to our friend, we're going to compile it first. We're going to compile it. We'd use the Go tool chain, so we'd write something like go build in our command line, and that would produce a new executable file, right? So this is machine code here. Let's just say that the name of our program is Hello World. Why not? So if we're on Windows, it might be helloworld.exe, right? So when you go online and you download a program to use, say it's a video game, it is probably a bundle of machine code. It is a built binary, right? In order to run your favorite video game, let's say StarCraft 2 or World of Warcraft, you don't need to install the C++ compiler, right? You're just given the built kind of final product, the final executable program. And that's what we're doing in the Go programming language as well. So now we can give our friend this executable. They don't need to install Go, and they do not need access to the original source code. So generally speaking, distributing programs that are natively compiled is much, much easier than distributing programs that kind of have a runtime dependency like an interpreter. So to answer the question for this exercise, do users of compiled programs need access to the source code? No, they don't. And a related question, which language is interpreted? We've got Go, C++, Python, and Rust, and the answer is Python. The rest are all compiled. So now the question is, why is it generally more simple to deploy a compiled server-side program or backend application? And the answers are compiled code is more memory efficient because Docker exists, there are no runtime language dependencies, or because compiled code is faster. Well, it's just the same as what we talked about earlier. When we deploy to a server, say on the cloud, we have to have all of the dependencies that our backend application needs in order to run installed on that server. And if there are no runtime dependencies, if all we need is a compiled binary, then that's arguably the simplest way to do it. right? So the answer is it's more simple to deploy a compiled program to a backend server if there are no runtime language dependencies, things like the Python interpreter or the Node.js interpreter, for example. Go is strongly typed and statically typed, and that's a really good thing. If you've been paying any attention at all to the JavaScript world, you'll notice that a lot of JavaScript developers are making the switch to TypeScript, and that's primarily to get access to static typing. A lot goes into typing and type systems, but one of the biggest benefits of a static type system like Go's is that when we declare a string, right, like say this username string that I've set equal to Wags Lane, we can't later accidentally change it to an integer, a number, right, like a float 64. It's going to stay a string. The nice thing about a static type system, like we have with Go or that you have with TypeScript, is that we get feedback on our errors much more quickly, right? Rather than finding out about a bug when our code is running in production, we find out about the bug, say, when we compile our code. Let's move on to the assignment. So the assignment says we'll be using basic authentication for the TextIO API. So basic authentication is just this format here where you've got a username and a password in an HTTP header. It tells the server on each individual request to the server who you are, right? It's kind of like logging in. Or rather, it's kind of like being logged in. Okay, so the code on the right has a type error. Change the type of password to a string. Okay, cool. So I'm just going to run it to see the type error first. So invalid operation, username plus colon plus password has mismatched types of string and int. Now, this is a compile time error. We weren't even able to compile this code, right? Let alone run it in production. So we've been instructed in the assignment, change the type of password to a string, but use the same numeric value so that it can be concatenated with the username variable. Okay, cool. So I'm just going to change this to a string by surrounding it in double quotes. That's how you do strings in Go. Pretty similar to other languages. And then I'm just going to change that type to a string type and run it again. Authorization, basic, Wags Lane, colon, number. That looks good to me. When we're talking about the performance of a programming language or an application, we really care about how it performs across two different axes. One is speed, how fast it can do computations, right, which is kind of measured in CPU cycles. And then we also have memory consumption, which is just how bloaty the program is, how much data it has to store in memory to be able to do those computations. Every program you write, no matter the language, is going to be using memory. Every time you create a new variable, it allocates space in memory where it can store that variable's data. Now, in languages like Rust or C, memory management is effectively manual. Now, that said, Rust does have some nice tooling that kind of takes care of it for you at compile time, so it's not quite as error-prone as it would be in C or C++. But at the end of the day, your program is allocating memory, right? It's saying, this chunk of memory I'm going to use. I'm going to store some variable data here in this bit of RAM. And then later, your program says, I'm not using it anymore, so we can free it up for use by other programs. Now, let's jump over to Java. So with Java, it's a little bit different. Java is a garbage collected language, garbage collection, which essentially means that memory management is automated. And in Java, it's done by the Java virtual machine. So every time you run a Java program, you're actually creating an entire mini virtual machine that your Java bytecode runs within. So this is the JVM. And then you kind of insert your code into the JVM, and you run your code in there. And the JVM is what takes care of allocating and freeing all of the memory that you use. And this creates overhead. Basically, at the end of the day, Java programs use quite a bit more memory than Rust or C programs. Go is in an interesting sort of in-between world where Go is a garbage collected language like Java, so it has automated memory management, but it does not have a JVM. When you compile Go code, rather than having to run it within a JVM, just like with Rust and C, you get one binary or one executable program. The difference is that Go includes a runtime within every single binary that's built using the Go programming language. So we could think of it as something like this. It's kind of like a little sidecar that is compiled alongside your code. So your Go program basically has this little bit of extra code that's added to it, and that bit of code is what handles garbage collection and automated memory management. So it's a little more bloaty than what you'd get with Rust and C, right? It is garbage collected, but it's not nearly as expensive in terms of memory overhead as a language like Java or C#. Let's take a look at what some actual numbers look like. I pulled this chart from Dexter Darwick's blog, and if you're following along on BootDev, you can click the link to go check out the full blog and the description of this experiment. But basically, he built a RESTful web server in 3 different programming languages, right? In Java, Go, and Rust, and then measured the memory consumption. And when the servers were just at rest, effectively doing nothing and waiting for requests to come in, Rust used less than half of the memory that Go was using, and Go used 100 times less memory, right, measured in megabytes, than the JVM was using to run the REST service. So to order the 3 languages in terms of memory efficiency, I would say Java is the least efficient, Go is in the middle, and Rust would be the most memory efficient. And it's also worth pointing out, just really quickly, that as the load on the server increases, I would expect Go to have more similar performance to Java. In other words, we wouldn't see as quite a large discrepancy here, right? Go would likely still be more memory efficient than Java, almost certainly, in fact, but it probably wouldn't be a 100x discrepancy. We're seeing this huge discrepancy mostly because this is a test of an idle program. So generally speaking, which language uses more memory? That's going to be Java. Another question on the same topic is, what's one of the purposes of the Go runtime? So to style Go code and make it easier to read, that doesn't make sense. That would be like compile time tooling, right? Not runtime tooling. To clean up unused memory, to cook fried chicken, or to compile Go code. So it's definitely going to be to clean up unused memory. And if you remember, the runtime is just that little bit of extra code that's included in every compiled Go program that, among other things, handles memory management. So we've already talked about how Go has strong and static types, but we haven't yet talked about what those types are. You're probably already familiar with Boolean values and string values, which are valid Go types and also exist in pretty much every other programming language. Numbers are where it first starts to get a little bit different if Go is your first compiled programming language. Generally speaking, numbers fall into 4 different buckets. We have integers, unsigned integers, or uints, floats, and complex numbers. Integers are just whole numbers. They can be positive or negative, right? 1, 2, 3, 4, you get the idea. Unsigned integers are the same as integers, but they're not signed, which basically just means they don't have a negative component. You can only represent positive numbers in an unsigned integer. You're probably already familiar with the idea of floats. It's just fractional numbers, right? Numbers that have a fractional component. Things like 1.21 or 3.14. Complex numbers are a little funny. They're used to represent the concept of imaginary numbers, if you've gotten to imaginary numbers in your math studies. I've never actually used complex numbers in production. I'm sure there are plenty of use cases for them, but we're not going to go into detail on how they work here. You can certainly go read up on it if you'd like. The only other thing worth mentioning is that size matters when it comes to types. A uint8 and a uint16 are 2 different types. They both represent unsigned integers, but a uint16 has twice as much room for data within it. It has 16 bits of data, whereas a uint8 only has 8 bits. For example, the largest number that you can store in a uint8 is 255, because that's the largest number you can represent with 8 ones and zeros in binary. But with a uint16, the largest number you can store is about 65,000. Again, because that's the biggest number that can be represented by 16 binary digits. Just like bigger number, better person, bigger number in your types means you can represent more possible values within that type. So float 64 can represent more values than a float 32. The only reason you wouldn't use a larger type is if you're trying to save on memory. If you're trying to write a program that is hyper performant, you'll want to use a smaller size, right? If you know that an integer is only ever going to store 3 different values, say 1, 2, or 3, then you might consider using a uint8. The byte type is an interesting one, and it's one that you'll use a lot, especially when you're, say, marshalling a JSON object to be sent across a network connection, or maybe you're reading to and from a file on disk. But under the hood, a byte is just an alias for the uint8 type, which makes sense, right? A byte is just 8 binary digits, 8 bits, and that's all a uint8 is. A rune is a Unicode code point, which generally speaking, you can think of as one character in a string, and that's usually how it's used. Under the hood, it's just an alias for the int32 type. Moving on to the assignment, it says initialize the given variables to int, float64, bool, and string respectively with their 0 values. And as we can see here, if we just use var, the name of the variable, and the type, that should do it. So we'll initialize the variables here. So var SMS sending limit is an int. Var cost per SMS is a float 64. Has permission is a bool. And username is a string. Okay, cool. And all of these variables are now instantiated and should contain their 0 value. So for example, 0, 0.0, false, and empty string. So let's go ahead and run that. And that looks correct to me. I'm going to go ahead and submit it. We've been declaring variables the hard way. Now we're going to do it the easy way. There is an operator in Go, :equals, that is the short assignment operator, and it allows us to declare variables and have Go infer their type. So instead of typing var empty string, we can just say empty : equals the empty string, and Go knows that this has to be a string. So it is a string. Now, when we use this short assignment operator, we're not saying this is a loose type that can change in the future. It's still a static type. Empty is a string, just like it would be if we declared it this way. In reality, in Go, you will very rarely see variables declared like this. You will almost always see them declared using the short assignment operator. For example, numcars : equals 10 creates a new variable called numcars and sets it equal to 10, and its type will be inferred to be an int. And the int type aliases either int32 or int64, depending on your computer's architecture. If you want to specify a particular size of integer, then you would declare it using this kind of longhand syntax. So in this assignment, we're just meant to declare a variable named congrats with the value happy birthday using a short variable declaration. So as simple as congrats : equals the string happy birthday. Let me run that. Perfect. This next assignment says our current price to send a text message in Textio is 2 cents. However, it's likely in the future that the price will have to be a fraction of a penny or have a fractional part to the cost. So we should use a float64 to store this value. Edit the pennies per text declaration so that it's inferred by the compiler to be a float64. Okay, cool. So here we're just setting it equal to 2. If I run that, then I get the type of pennies per text is int. And this %t in Go is a formatting verb that tells the Go programming language, or at least the printf function, I should say the formatting package from the standard library, that I want to print the type of this variable rather than its value. So that's why we're seeing int there instead of 2. To get a float, all we need to do is change it from 2 to 2.0, I believe. Float64. Cool. Another handy syntactic quirk of the Go programming language is that we can declare multiple values on the same line. So in this assignment, it says declare a float called average open rate and a string called display message on the same line. Okay, so average open rate, display message, same line. The average open rate must be 0.23. And the display message should be the string is the average open rate of your message. And then it looks like this is just going to print them together. So it's going to say 0.23 is the average open rate. Okay, cool. Let's go ahead and run that. 0.023 is the average open rate of your messages. That looks correct to me. So we've already briefly talked about the different type sizes in Go, right? So we have the int type, int8, int16, int32, and int64. And it's important to understand that the int type just aliases int32 or int64. Same with the uint type, just depending on your CPU's architecture. So you might be on a 32 or a 64-bit machine. Most modern machines are going to be 64 bits. My recommendation is that unless you have an explicit reason to care about the size, right? So unless you're trying to kind of hyper optimize for performance, then you should really just stick to these 4 types: int, uint, float64. And again, if you're working with imaginary numbers, then complex 128, but that's honestly unlikely. So these 3 types are going to do the vast majority of the heavy lifting when it comes to working with numbers in Go. We can also convert numbers between, different number types. For example, we could take an integer, 88, and convert it to a float like this. So it'd become 88.0, right? Converting the other way is a little trickier though, because say we had 88.6, if we were to convert it to an int, we would lose the 0.6. We would truncate it down to just 88. Now, this assignment says, our Text.io customers want to know how long they've had accounts with us. Follow the instructions in the comment provided. You will create a new variable called accountAgeInt that will be the truncated integer version of accountAge. Okay, cool. So create a new accountAgeInt here. Should be the result of casting accountAge to an integer. So we'll just do int accountAge, and I would expect that to be 2 after casting it because it should truncate the 0.6. So let's go ahead and run that. Your account has existed for 2 years. Yeah, that looks good to me. We already briefly touched on this, but it's worth mentioning again. I recommend that you stick to I call them the default types. So for example, we know there's, 5 or 6, I can't think of it off the top of my head now, different types of ints, right? Int, int8, int16, int32, int64. I'd recommend sticking to int unless you have a very good reason to specify a smaller size, like int8 or int32. And that's simply so you avoid cluttering your code with tons of type conversions that can sometimes even lead to bugs. So unless you need a smaller type for performance reasons, just use these default types. Okay, so the question for this assignment is, when should you elect to not use a default type? When either a default or a specific size will work, when my system has lots of extra hardware that I want to utilize, or when performance and memory are the primary concern. So it's going to be performance. If you have performance concerns, that's the time I would maybe stray away from the default types. The next question is, what does the size of a type indicate? So a float 64, what does 64 mean? Is it bits, bytes, or nibbles? The answer is going to be bits. Now, it is worth pointing out, nibbles is a real thing. So a byte is 8 bits, a nibble is actually 4 bits. If you didn't know that. Fun, interesting trivia. Aside from variables, Go also supports constants, which are immutable values. And in Go, just like in JavaScript or TypeScript, we use the const keyword, and constants do not support the short declaration syntax. So we have to kind of write it all out. Okay, so getting to the assignment says use 2 separate constants. Something weird is happening in this code. What should be happening is that we create 2 separate constants, premium plan name and basic plan name. Right now it looks like we're trying to overwrite one of them. Okay, cool. So on line 6, we've got premium plan name, and we're setting it to premium plan, and then we have premium plan name again, attempting to override the value and set it to a new string. If we try to run this, we actually get a compile time error. So we're not allowed to mutate constants in Go. So what we should be doing is creating a separate constant, and it should be named basic plan name. Let's go ahead and run that. Plan, premium plan, plan, basic plan. Looks good to me. Constants in Go are not the same as constants in JavaScript and in TypeScript. In JavaScript and TypeScript, the const keyword really just means you can't reassign to this variable, but you can compute the variable or the variable's value at runtime. In Go, every value that's stored in a constant must be known or computed at compile time before the program runs. So if we create this new constant called myInt and set it equal to 15, within the compiled Go binary, effectively this symbol, myInt, just refers to the static number 15. The cool thing is that we can actually compute constants. Like we can make constants that depend on other constants, but that computation will run when we compile our code, not when we run our code. So for example, I can create this constant first name, Lane, last name, Wagner, and then I can create a new constant called full name. It's first name plus a space plus into last name. And that's really convenient in case I ever want to change first name. Now I don't have to change it in two places, right? Full name will automatically update. But this is only valid because all of the inputs to this full name constant, first name and last name, are known at compile time. So the compiler can still do the thing it wants to do, which is replace full name with a static string, right? Lane space Wagner. So on to the assignment. It says keeping track of time in a message sending application like Textio is critical. Imagine getting an appointment reminder an hour after your doctor's visit. Not very helpful, right? Complete the code using a computed constant to print the number of seconds in an hour. Okay, so we've got the number of seconds in a minute is 60. The number of minutes in an hour is also 60. So how many seconds are in an hour? Cool. Well, we could hard code this as like 60 times 60. But the cool thing is we can actually compute it because we can say, well, we know the number of minutes in an hour, and we know the number of seconds in a minute. And if we multiply those two together, we should get the number of seconds in an hour, right? That looks correct to me. So I'm obviously a huge Go fan, but formatting strings in Go is honestly one of my least favorite features of the language. I think it's one of its weaknesses at the moment. Who knows? Maybe it'll improve in the future. The way it's done, well, we essentially have two different functions provided to us by the standard library. We have printf and sprintf. Printf prints a formatted string directly to standard out, and sprintf just returns the formatted string as a value. Basically, all string formatting in Go currently works the same way. We have these formatting verbs, things like %v, %s, %d, and they're replaced in the string template with actual values. So for example, I am %v years old. The %v in this case is replaced by 10, the first parameter that comes after the template in the printf function. Here we could also replace with a string instead of an integer, right? I am %v years old. Way too many. Prints I am way too many years old. %v is sort of the default formatter. It's usually what you want. Assuming you don't want to print in kind of the default standard way using %v, then there are a few others. %s interpolates a string. %d interpolates an integer in decimal form. So for example, 10 becomes the number 10 instead of, say, in binary form. %s is for floats, so you can specify the number of kind of places after the decimal point that you want printed out to the console or printed out to the returned string in the case of sprintf. So I actually do end up using %f fairly regularly when I'm working with floats. So onto the assignment. It says create a new variable called MSG on line 9. MSG stands for message, of course. It's a string that contains the following. Hi name, your open rate is open rate %, where name is the given name and open rate is the open rate rounded to the nearest tenths place. Okay, so the tenths place is the number right after the decimal. So let's get started here. Message : equals fmt.sprintf. So we're going to use sprintf instead of printf because we don't want this value going to standard out. We want it returned from the function. So we can save it in the MSG variable. Let's just grab this template. So we'll use %s. We could use %s or %v here because we're just interpolating a string. And we'll do percent 0.1f because we want to just print the first number after the decimal point, right? The tenths place. Okay, and then we just pass the two values as the following parameters, or as the last two parameters. So name and open rate. All right, so the first value, name, will go into the first verb. The second value will go into the second verb. Let's run that, see what we get. Hi, Saul Goodman, your open rate is 30.5%. That looks good to me. Let's talk about conditionals in Go. So a conditional is just where we are checking if a condition is true. If it is, we do one thing. If it's not, we may do another. So for example, here's an if statement in Go. And if this expression evaluates to true, then we'll run the stuff within the curly braces, the body of the if statement. If you're familiar with other programming languages like JavaScript, this is a very, very similar syntax. The only difference is we're not surrounding the height is greater than 4 section with parentheses. So again, to be clear, this bit between the if keyword and the curly brace will be evaluated. And if it evaluates to true, then the stuff inside the curly braces will be executed. So in this case, we have the variable height, and we're using the greater than operator to compare it to the number 4. So if height is greater than 4, then we'll print you are tall enough. I've sort of listed some of the different comparison operators down here at the bottom. They're basically identical to pretty much every other programming language you will probably have used up to this point. Additionally, we can do different things if the if statement does not evaluate to true. So this is a perfectly valid if statement. You do not need an else if or an else block. They're optional, effectively. But the way it works is when we get to this code, basically we'll compare height to 6, right? And if that expression evaluates to true, then we'll just print you are super tall and we'll be done. Okay. Otherwise, if that expression evaluates to false, then we'll drop down into this next else if statement, and we'll compare height to 4. If height is greater than 4, then we'll print you are tall enough. And again, we'll be done at that point. So if this evaluates to true, we execute this kind of section of code between the curly braces, and at that point we'll be done. Otherwise, if that's also false, so if height is not greater than 6 and height is not greater than 4, then the else statement executes. Notice the else statement does not have its own expression. It just kind of always executes if all of the if and else if statements turned out to be false. So let's jump into the assignment. It says fix the bug on line 12. The if statement should print message sent if the message length is less than or equal to the max message length, or message not sent otherwise. Okay, cool. So up here, we've defined two variables. Message length is 10, max message length is 20. And then here we're going to do some comparing. Let me just run the code in its current state. It says trying to send a message of length 10 and a max length of 20. Message not sent. Okay, so that seems problematic, right? Because with a message length of 10 and a max message length of 20, I should be able to send that message. So the bug on line 12, I think we just need to flip this operator to be less than or equal to, so that now this expression, right, message length less than or equal to max message length, should evaluate to true, because message length is in fact smaller. Okay, let's run that. Message sent. That seems to work. It's worth pointing out that in Go, we also have kind of an alternate way to write if statements. If the variable that we're comparing in an if statement is only used in that if statement, then this syntax can be helpful. Okay, so here's kind of the traditional way of doing something. We would create a variable called length. Let's just assume it's an integer. You can kind of forget this function syntax for now. We'll talk about it in a future chapter. But basically the idea here is we have a length variable, it's an integer, right? And we're initializing it here. We're creating the variable here. And then we're comparing it against 1, right? We're checking if it's less than 1. And if it is, we're doing something. In this case, we're printing that the email is invalid. Well, instead of this syntax, and by the way, this works perfectly fine. There's nothing wrong with doing it this way. But we can alternately do it this way, which is basically to initialize that length variable in the if block within that first kind of initial statement. So notice there's two statements here separated by a semicolon. And in the first one, we're creating that length variable. And then we're moving the comparison itself kind of after the semicolon. And then if that condition obviously evaluates to true, then we'll execute the block. This does kind of two things for us. First, it saves us a line of code, which I would argue probably isn't the biggest benefit in the world. But more importantly, it makes it so that this length variable is only accessible within kind of the scope of this if block. So kind of down underneath this code, we wouldn't be able to use the length variable anymore, which is kind of nice if you never intended to use it in the first place. You can kind of think of this as a clean code hack or like a kind of safety hack to ensure that the length variable is never reused down below in other code when you never intended it to be reused. Okay, so the question for this assignment is, why would you use the initial section of an if statement? And the answers are to confuse other programmers, to keep the code concise and the scope limited, or to speed up your code. The answer is going to be to keep the code more concise and to, again, limit the scope that that variable exists within. Like other programming languages, Go supports functions. Functions are basically just a way to break up your code into individual units that are easier to reason about, right? A function takes in a specified number of inputs and it returns a specified number of outputs. For example, this subtract function here, named sub, takes two inputs, x, an integer, and y, an integer, and it returns a single integer. And in this case, it just performs the simple calculation x minus y, and then returns the result to the caller. Now, this little bit right here, right, func sub x integer, y integer, returns integer, is what's known as the function signature. If you've never heard that term before, it's basically just a description of what the function does in terms of its types, in terms of its inputs and its outputs and what types they are, right? This basically says this is a function called sub. It takes an integer x and an integer y and returns another integer. Function signatures are great because they tell us how we can use the functions. Really, at the end of the day, if we're the person calling the function or the person using the function, really all we care about is what we need to give the function as inputs and what we get out of the function in terms of its outputs. So a function signature basically tells us all we need to know about a function to be able to use it. It omits all of the implementation details, the stuff within the curly brackets or within the body of the function. So let's get on to the assignment. Assignment says, we often need to manipulate strings in our messaging app. That makes sense, right? We're working with SMS and email messages within Textio, so we're doing a lot of textual data manipulation. The concat function should take two strings as inputs and smash them together, right? So returning a new string that is a concatenation of the inputs. For example, hello plus world equals hello world. So we'd expect to return this concatenated string from our concat function over here. Fix the function signature of concat to reflect its behavior. Okay, cool. So let me try running this and just see what happens. Looks like undefined S1, undefined S2, undefined S1. Okay, so these are undefined. And so S1 and S2, that kind of stands for string 1, string 2. That makes sense. The problem here is that we're not telling Go what the types of the inputs should be. And this plus operator, when operating on strings, just concatenates, so that should work. Let's go ahead and run that. Yeah, this looks good to me. I want to just make one more point about function signatures in Go. You'll notice that the type comes after the name of the variable. So S1 is a string, S2 is a string. And that's just to make it a little easier to read. The authors of the Go programming language kind of built on a lot of the ideas from C, and in C it was the reverse. It was string S1, string S2, and that just kind of reads a little clunky if you're used to kind of speaking in plain English. It makes more sense for the type to kind of come after what it describes. Go provides another bit of interesting syntactic sugar when it comes to function signatures. When multiple arguments are of the same type, in this case x and y, the inputs to the add function are both integers, the type only needs to be declared on the last one, assuming that they're in order, right? So in this case, this is valid Go code, and x and y are both integers. Because they follow one another, we can put the integer just after the y. If we were going to add, say, a string as a third parameter to this function, then we would just add a comma here after int and put, name, string, or whatever. This is just a bit of syntactic sugar. It makes our code a little less verbose. You don't need to do this. You can explicitly put the type on every input and output, but you will often see code like this. It's a convenient shorthand. So we've got these two example snippets of code. Func create user, first name string, last name string, age int, and func create user, first name, last name string, age int. So which of the following is the most succinct way to write a function signature? Succinct is just another word for kind of, I guess it's the opposite of verbose, right? Fewer words. It's going to be the one that uses the syntactic sugar, which is this one, because we're omitting the string keyword after first name. So we already talked about this briefly, the idea that in Go, we specify the type of a variable after the variable name. And this is, different from kind of the C style way of doing things, which if you were to declare a variable y in C, you would say int y. And really, the authors of the Go programming language just felt that that didn't flow naturally from English. It's not the way we talk, right? We say x is an integer, not integer is x. If you want to read up on that decision and why they ended up choosing that style, then you can follow this link here, assuming you're following along on bootdev. So the question is, what are we talking about when we discuss this declaration syntax, right? This swapping of the name and the type. And here are options: the decision about camel case versus snake case, the style of language used to create new variables, types, and functions, guard clauses versus if else. No. The ever important question of tabs versus spaces. No, it's going to be the style of language used to create new variables, types, and functions. Related question is, which language's declaration syntax reads like English from right to left? C or Go? The answer is going to be Go. Go supports functions as data, or basically the idea that you can pass functions around your program to be called in different places. Callbacks, right? If you're familiar with JavaScript, then you're probably familiar with the idea of a callback. It's a function that you could pass to another function to be called later. This question deals with that idea. Whenever we pass a callback in Go, the type of the function changes based on what its inputs and outputs are. So for example, here, func int is a function that takes two integers as an input and returns an integer. And that's going to be a different type than a function that, say, took three integers as input and returned an integer. And if you think about it, it makes sense, right? If I'm going to pass a function to another function so that it can call it later, it kind of needs to know how many inputs, how many parameters it can pass into that function. If it's a function that takes two inputs versus three inputs, then the caller is going to have to write the code differently. So we have to treat every function signature as its own unique type. So this question's a bit of a doozy. I encourage you to pause the video and try to work this one out on your own. But basically it says, what is this hairy beast here, right? F, func, int. All right. Potential answers are a function named F that takes an int as the argument and returns an int. No, it is not nearly that simple, right? A function named F that takes a function and an int as arguments and returns a function. Let's see. That right there is a full function and an int as arguments and returns a function. No, this returns an int. Okay, a function named F that takes a function and an int as arguments and returns an int. That's what I believe it will be. Function named F that takes a function as the argument and returns an int. Yep, that's not it. So to be clear, F is a function. It takes two parameters. A function, right? A function of a specific type, a function that takes two ints and returns an int. And as its second parameter, an int, and then F returns an int. Hopefully that makes sense. Again, feel free to pause the video and stare at that for a second. Let's talk a little bit about memory and how data that we create in our program using variables is stored in memory. So over here, I'll keep track of the memory of our program, and over here I'll write some code. So let's say in our code, we write x equals 5, right? So we're creating a new variable called x, and we're giving it the value, the integer value of 5. And then we're placing the value 5 in that memory, right? Stored as binary data within RAM. Now in our program, x, the symbol, is essentially just a pointer. It points to this location in memory. So let's say on the next line of code, we update x and we say x equals 2. So now we're reassigning the value of x to 2. Now let's try something different. What if we create a new variable called y and we initialize it to the current value of x, which in this case happens to be 2? Well, in this case, we're actually going to allocate a new section of memory to store the value of y, and we'll initialize it to the current value of x, which is 2. And the symbol y now has its own location in memory. So we basically created a copy of x. Now, this idea is really important to understand because sometimes in programming, we'll have multiple variables that actually point to the same location in memory. They can overwrite each other. And sometimes we don't. Sometimes we have copies of data, right? So now, for example, if I were to update y, let's say I made y equal 1. At this point, x would be unaffected, x would remain 2, but y now becomes 1, right? Because we have a copy. These two variables, x and y, reference different locations in memory. So why does all of this matter? Well, in Go, variables are passed by value, not by reference. So let's take a look at this code snippet here. Top of main, we declare a new variable called x, we set it equal to 5. And then we pass x into a function called increment. The increment function just adds 1 to x, right? Making it 6. After that, we print x. And the weird thing is that when we print x here, we still get 5. And the reason for that is the increment function was operating on a copy of x. When we pass x in here to increment, increment gets a new copy of x, still equal to 5. It increments that x to 6, and then because we are not returning it, it essentially just gets thrown away. And then back in main, we still have this same x that's still equal to 5. The correct thing to do here would be to have the increment function return x after making its modification, and up in main, we would write x equals increment x so that we could capture the return value from the increment function. So moving on to the assignment, it says it's critical in Textio that we keep track of how many SMS messages we have sent on behalf of our clients, fix the bug to accurately track the number of SMS messages sent. Okay, let me just try running this in its current state. And we're missing a return. Okay, I'm gonna remove this type return there and see what happens. Sent 430 messages. And it looks like here we have sends so far, sends to add, increment sends is doing nothing because sends so far is still printing as 430. Okay, I think I'm understanding. So let me put that back in. The assignment says alter increment sends so that it returns the result after incrementing sends so far. Alter the main function to capture the return value from increment sends and overwrite the previous sends so far value. Okay, cool. So this is pretty similar to the code snippet here. Basically, we need to return an int. So we're going to return sends so far. And then here, we need to reassign sends so far into the result of increment sends. Cool. So again, here we'll still be operating on copies, but because we're going to return the copy and save it back into the original variable, we should be good to go. Let me run that. Yep, you've sent 455 messages. That looks correct. Functions in Go can have multiple return values, and when they do have multiple return values, the syntax for specifying that is just to wrap the return values in parentheses as well. So when there's just a single return value, we do not wrap that return value in parentheses, but when there are multiples, we do wrap them in parentheses. One thing I really like about Go is that it does not allow you to have unused variables. And because it doesn't allow you to have unused variables, and because it allows you to have multiple return values from a function, we kind of need a way to ignore some of the return values, because there are definitely instances where a function returns two things, but maybe we only care about one of those things. For example, a point on a graph can be described by its xy coordinates, but maybe all we care about is the x coordinate. So here we can call the getPoint function and ignore the y value by using an underscore. And it's important to understand that the underscore is not just like a conventional name that we are going to ignore. It's actually ignored. The compiler completely removes it from our code. So moving on to the assignment, here in Textio, we have obviously first names and last names for all of the users that we're able to send messages to. Well, when we welcome someone to Textio, we don't need their last name. So let me go ahead and try to run this code. And you'll see we'll actually get a compiler error that says last name declared and not used. Like I said, Go does not allow us to have unused variables, which I think is kind of an awesome little bit of the tooling. It helps keep our code very clean and concise, easy to understand. So we need to explicitly ignore that last name with an underscore if we're not going to use it. Let me try running that again. And that looks good to me. In Go, we can name our return values, and if we do, it actually alters the behavior of the function just a little bit. Let's take a look at this function, getCoords or getCoordinates. It returns two integers, and we've named the integers x and y. And by naming them, we've actually initialized at the top of the function the variables x and y, and they're initialized with their 0 values. So in the case of an integer, literally just the number 0 for both of them. The other interesting thing about naming our return values is that if we use a naked return statement, a return statement that doesn't explicitly say, for example, return 0, 5, then the values of x and y are automatically returned from the function. So this version of getCoordinates is actually the exact same as this kind of more verbose version of getCoordinates, right? Here we have not given the return values the names x and y, and instead we've initialized x and y to their 0 values and then returned them explicitly. Now, a couple of recommendations. I would recommend using named returns when you want to document kind of what the intended purpose of each return value is. So for example, if you have a function that just returns 3 integers, that function signature could be pretty confusing. But if you have a function signature that says it returns 3 integers and they're named width, height, and length, that's a lot more interesting to the caller of the function. They understand the purpose of each individual return value much better. So I like to think of named return values as basically a built-in way of documenting what the purpose of all of your return values are, and you should generally just use them. On the other hand, this implicit or automatic return that you get along with named return values, I would typically advise against. You'd only want to use this in like very short, very simple functions because it harms readability, right? And I'm pulling this directly from the tour of Go. They also agree with me. Implicit returns or naked return statements, generally a little bit harder to understand. So the way I would write this function personally would be getCoords, x, y, int, and then I would explicitly return x and y. So let's jump down into the assignment. It says one of our clients likes us to send text messages reminding users of life events coming up. Fix the bug by using named return values in the function signature so the code will compile and run as intended. Okay, cool. So this is the function we are interested in fixing, years until events. Looks like it takes a user's age as input and then returns or should return kind of the number of years until they're an adult, which is 18, the number of years until they can drink, at least in the US, which is 21, and the number of years until they can rent a car, which apparently is 25. And it looks like we never want a negative number. So if any of these are less than 0, we just set them equal to 0. That makes sense. Once you're over 18, your years until you're an adult are just 0, right? You're already an adult. Okay, let me try running this, see what we get. Okay, undefined years until adult. All right, this makes sense, right? Because there's no colon here, so we're not defining a new variable. And the assignment said to use named return values. So let's go ahead and do that. So years until adult, years until drinking. I'm gonna format this a little better. And we'll do years until car rental. So again, this will declare all of these values with their 0 value at the top. And then this naked return statement should return them in order. And just to make sure, adult, drinking, car rental, adult, drinking, car rental. Okay, we're in the right order. Let me run that. First test. So 4 years old, they'll be an adult in 18 years, can drink in 17, can rent a car in 21. That all looks good. 10, it's going down. 22. Yep, this looks good to me. So as I mentioned before, explicit returns are probably better than implicit returns in most scenarios. It just makes a lot more sense, right? So here in this function, getCoords, x, y, int, so we're using named returns, but we're still explicitly returning x and y. This is how I would recommend writing most of your Go code. This function here is doing the same thing. It's explicitly returning hard-coded values, though, instead of the variables x and y. And it's just important to understand that this effectively overrides the implicit return of x and y. So in this case, 5 and 6 will be returned. Again, that's why I recommend doing it explicitly, because when you see a return statement that has explicit values being returned, those are the ones that are returned. You don't have to do any guesswork. You don't have to scroll back to the top of the function to see which values are being returned. So now we're going to break that advice just for practice's sake. The assignment says fix the function to return the named values implicitly. Okay, so here we have a problem in our code where we are basically explicitly returning zeros, which, as we talked about, overrides the implicit return. So my guess is if we look at all of these, yep, every test is returning zeros. If we just remove that implicit return and run that, and it should work as intended. Yep. And then just to show you what I mean, like what I would recommend doing is this. It's bigger. Like that. That's how I'm going to recommend doing it. And in fact, because bootdev just checks the output, this should work just fine with our tests. So I'm going to submit it like this. Moving on to some questions about named returns. So it says, when should naked returns be used? And the answers are for large functions, for small functions, or for complex functions. And I would argue if you're going to use naked returns at all, which honestly I'd kind of just recommend against, then you should only use them for small functions. The more complex and large your functions get, the more important it is to be explicit and readable and document your returns with named returns and things like that. The next question is, when should named returns be used? So when there are many values being returned, when the function is simple, or when there are few parameters being returned. I would argue it's never really a problem to name your return values, but it's really important when there are many values being returned, especially if there are many values of the same type being returned, because then you can essentially tell the caller of your function through your function signature what they should expect each value to represent. Let's talk about one of my favorite programming patterns or programming styles. That is early returns, or what they're also sometimes called as guard clauses. So an early return or a guard clause is exactly what it sounds like. It's just when we return early from a function. So this function divide, if it's past a divisor of 0, then it returns early with an error. Otherwise, it goes ahead and does kind of the division and returns the results and a nil error. Now, we're going to talk about errors soon. You don't have to worry too much about how they work for now. Just understand that a nil error effectively means no error. So when we're looking at this divide function, we can understand that if the divisor is 0, we're going to return early and it basically say we can't do this division because we can't divide by 0. Otherwise, we'll take the happy path towards the end of the function. Best practices when it comes to software engineering and how we write code change all the time, right? There's millions of developers all around the world writing code, and we all have different opinions, and kind of the common opinion about a certain style tends to change over time. The interesting thing is, I think that these days, guard clauses and early returns are kind of looked at as a good thing. This is clean code, right? This is a good way to write code. Certainly most Go programmers think this way, but it wasn't always that way. There used to kind of be a heuristic that developers used, which was you shouldn't ever return from a function in more than one place. So back when that was kind of the more popular way of doing things, you'd get kind of nasty if-else nested statements like this. If you look at this function, get insurance amount, basically takes a status as input, it returns an integer, and it only has one return statement. So it only returns from one place. But I would argue that doesn't necessarily make this function all that much easier to understand, right? We're initializing a variable up at the top, amount, and then just in this big, nasty, nested if-else chain, we're kind of reassigning the value of amount based on some conditional logic. Now, compare that with guard clauses. Right? So with guard clauses, instead of overriding the variable amount and then returning it at the end of the function, we're just returning early with the proper amount at each step of the way. Now, both of these functions do the exact same thing. They have the same behavior. But I would argue that the one with the guard clauses is much easier to understand. So the question for this exercise is, which is true? Guard clauses are unreadable. Guard clauses are generally worse than nested if-else statements, or guard clauses provide a linear approach to logic trees. Okay, so it's definitely not these two, right? So I'm going to go with provide a linear approach to logic trees. And really all that means is rather than having to follow kind of a tree structure to look at conditional logic, we can just follow a straight line, right? Is it this? No, we move on. Is it this? No, we can move on, right? It allows us to break up kind of the cognitive load when we're reading code. So definitely a linear approach there. The next question is, what is a guard clause? So a bitwise OR operation, an AND operation in Boolean logic, or an early return from a function when a given condition is met. And it is an early return. Let's talk about structs. So structs are the first collection type that we're going to talk about in this course. A collection type is just a type that contains other types. In the case of a struct is just a collection of key value pairs. If you're familiar with Python dictionaries or JavaScript object literals, this is basically the same idea. So for example, we can define a car struct, and we can say a car has a make, a model, a height, and a width. And each of those fields has its own associated type. So let's move on to the assignment. I think looking at the code is going to be the easiest way to understand structs. Okay, complete the message to send struct definition. It needs two fields, phone number, an integer, and message, a string. And on these exercises, I always recommend kind of going and looking at the test suite. This is all the code. The way BootDev works, like all the code is here, and we're really just testing standard output to see if you got the right answer. So you can see literally everything that's going on. So here you can see where a message to send is going to be instantiated with phone numbers and messages. And here you can see where it's the if fields are going to be accessed with the dot operator. So let me go ahead and run it in its current state. We should get, a compile time error where it's saying message is undefined, phone number is undefined, right? So we need to add those to the definition. All right, phone number, integer, message, string. Let's go ahead and run that. And sending message, love to have you aboard to that big number. Okay, that looks good to me. Struct keys can hold any type, not just primitive types like integers, strings, and booleans. Here you can see we've actually nested the wheel struct within the car struct, right? So we have the car struct from the last example, and we've added a front wheel and a back wheel, and they are each of type wheel, right? And a wheel has a radius and a material. So we can actually nest structs within other structs. And then we also saw this just a little bit in the last assignment, but this is how we can instantiate a new instance of a struct, right? So This is the struct definition. We're saying this is what a car looks like. And then here we've created a new empty car called my car. And when you create it kind of with those empty brackets, all of the fields inside of the struct will just be initialized to their default values, their 0 values, right? So strings will be empty strings, ints will be 0. And then here we're using the dot operator to access fields, right? So my car dot front wheel, right? So we're accessing the front wheel key, and then dot radius to access the radius within the front wheel, and we're setting it equal to 5. Again, with this syntax stuff, it's just best to get hands on keyboard and jump right into it. So let's get to the assignment. It says Textio has a bug. We've been sending texts with information missing. Before we send text messages in Textio, we should check to make sure the required fields have non-zero values. Notice that both the user struct, so that's this here, is a nested struct, or notice that the user struct is a nested struct within message to send. Okay, so message to send has a message, which is a string, and then a sender and a recipient. And both of those are of type user. Okay, that makes sense. A user is the sender, a user is the recipient, and then there is a message. Cool. Complete the can send message function. Okay. It should only return true if the sender and recipient fields each contain a name and a number. If any of the default 0 values are present, return false instead. Okay, cool. So can send message. This is essentially a function that's going to validate a message to send to see if it actually has data inside of it. So if I run the code right now, it's always returning true, right? So you have an appointment tomorrow, you have an event tomorrow from Susie Saul. See, there's a phone number missing there. That's a problem. Looks like there's a phone number missing there. That's a problem. Okay, let's see. So sender and recipients contain a name and a number. So if m to send dot sender and recipient, sender contain a name and a number dot name is empty, return false, right? And then if m's dot, it's going to be recipient is empty, also return false. So we're just going to do some guard clauses here. And then sender and recipient, and now we're interested in the number. Number is an integer, so if it's 0. Cool. So we're just basically doing a very simple validation to make sure that names aren't blank and numbers are not blank. So let me run that. Okay, so this one has all the information there and it's sent. Now this one has a number missing, can't send message. That looks correct. Okay, this is looking good to me. All right, next up we have anonymous structs. So anonymous structs are just struct instances that don't have a name. So whenever you create a new anonymous struct in Go, you're immediately instantiating a struct of a given type, right? The type of the struct doesn't have a name. So for example, here we have a struct with a make and a model. Now in the exercise previous, remember we actually had this same exact struct, but we'd given it a name. The name was car, right? Here, we haven't created a new struct definition. We haven't created a new struct definition called car. Instead, we're immediately instantiating a new instance of a struct called myCar. This could be named anything, right? And it just has a make and a model field on it. So the only reason you would use an anonymous struct is if you have no reason to create more than one instance of the struct. So to be clear about what's happening here, we're creating a new variable called myCar, and it has 2 fields. It's a struct with 2 fields, make and model, and we're immediately giving it a value of make Tesla Model 3. And this type, this specific struct type, doesn't exist anywhere else within our program. This is kind of a type that's just unique to this one instance called myCar. It's not very common that you'll see kind of top level anonymous structs like this. More often, you'll see nested anonymous structs, right? So rather than creating wheel as a separate struct type, we've just said, well, wheels kind of always exist within cars. I know that's not really true, but maybe within our program it's true. So we just create a little anonymous struct within the greater car struct. Now, as far as best practices in writing clean code, my opinion is that you should generally favor named structs. You avoid anonymous structs unless you have a really good reason to use them. You'll really never go wrong with naming your structs. Okay, so the question on this assignment is, what is a good reason to use an anonymous struct? You're worried about security, you need your code to be faster, you're worried about user privacy, or it is only being used once. Well, the only thing even remotely related to how anonymous structs work is that it's only being used once. So if you're certain that you only want this type to be used one time, maybe you don't want someone accidentally reusing a type, then you might want to use an anonymous struct. Next question is, what's one advantage of using an anonymous struct? Anonymous structs make your code run faster, anonymous structs prevent you from reusing a struct definition you never intended to reuse, or anonymous structs can be compiled more quickly. It's this reuse one. One place that I have used anonymous kind of top level structs from time to time is in HTTP handlers. So if I know that a given HTTP endpoint will always return a specific JSON payload, then I'll use an anonymous struct to define the shape of that JSON payload. We haven't really talked about JSON in Go yet, but kind of spoiler alert, structs are how we structure JSON data typically. Next, we have embedded structs, and embedded structs are not the same thing as nested structs. An embedded struct is basically where we take all the fields from one struct and kind of shove them into another one. Let me show you what I mean. So here's our car struct that we've been using for our examples. It's got a make and a model. Great. Here's our truck struct. Now you'll notice we've embedded the car type here, but the car is missing kind of a name, a key in the truck struct. The bed size is the key, int is the type. Here we just have the type, which is car. So what does this do and how does it differ from a nested struct? Well, in the embedded struct, if we want to access the field model from an instance of a truck, rather than doing truck.car.model, we would just do truck.model. Because these fields of the car type are becoming kind of top level fields of the truck type. We're inheriting all of those fields from the car type. Now, I have to be careful with the word inherit, even though it is kind of a pretty good descriptive term for what's happening. Go is not an object-oriented language because it doesn't support classes or inheritance in the class-based sense. So if you're familiar with the idea of object-oriented programming, just know that classes and inheritance aren't really what's going on here. You could almost just think of this as a shorthand for kind of retyping this make and model into the truck struct. It's almost just a syntactic sugar so that we don't have to retype all of these fields. So let's take a look at some code and how we would use this truck struct. So I've created this new instance of a truck, call it lanes truck, has a bed size, which is an integer, right? And it has a car here. Now you might look at that and say, that looks an awful lot like a nested struct. And the syntax for creating a new instance of an embedded struct is very similar to the syntax for a nested struct. Essentially, the key is just the same name as the type. It's just kind of a quirky thing about composite literals. The embedded stuff looks like the nested stuff. However, when we're accessing the individual fields on lanes truck using the dot operator, you'll see they're all accessed at the top level. It's not lanes truck dot car dot make, it's lanes truck dot make, right? It's not lanes truck dot car dot model, it's just lanes truck dot model. So those fields are being brought up into the top level. It's just when we kind of instantiate the truck the first time that we need to do this sort of nested syntax. So let's hop into the assignment. It says at Textio, a user, which is a struct, represents an account holder, and a sender is just a user with some additional sender specific data. A sender is a user that has a rate limit field that tells us how many messages they are allowed to send. Fix the system by using an embedded struct as expected by the test code. Okay, so let's go ahead and take a look at the test code. So it looks like the test code is creating some senders. And it's expecting that a sender has a rate limit and that it has a user, right? And this is looking like an embedded struct. And up here, you can see S is a sender, and we're directly accessing name, number, and rate limit all at the top level. So I think all I need to do here is embed the user struct. In fact, let's run this without that, see what happens. Yep, we're getting some undefined fields. We'll embed the user type in there. And that's looking pretty good to me. I will mention, just to give you an idea of like when you use this in the real world, one place that I use it actively on boot dev is users have kind of public fields on boot dev and private fields. So public fields are stuff that we show on the leaderboard, things that kind of anyone can see about your profile, maybe your bio or your profile picture. But users also have private fields, things like your hashed password, right? The password we store in the database. And I've actually embedded the private fields within the public user so that I can easily nullify them when I don't want to send private data to a given web page. All right, let's go ahead and run this code. Let's talk about methods on structs, or just methods in general in Go. I know I told you Go is not object-oriented, and it's not, but if you squint really hard, structs in Go kind of look like classes in a language like Java, JavaScript, or Python. So methods in Go are just behavior, or functions, that we can define on a type. And more often than not, we end up defining methods on structs, although we could define methods on any type. So let's take a look at the syntax for this. So here we have a simple rectangle struct. It has a width and a height, right? And here we've defined an area method on the rectangle struct. So this is just a function, right? We're familiar with functions already. The only difference is that we've added this special parameter before the name of the function, which is, again, just a parameter that comes into the function. It's just a special parameter. In this case, it is of type rect, which is just a struct, and we've named it r. And then this function just returns r.width times r.height, right? So it returns the area of the rectangle. So why would we use a method on a struct? Well, there are reasons that we'll get to later when we talk about interfaces, but for now, it's mostly a syntactic thing, a syntactic sugar thing. If we have behavior that we want to define on a given type, then structs can be a really good choice. They give us this nice syntactic sugar, right? We create this new rectangle called r, and now we can just call r.area to get the area of the rectangle. It's kind of a nice way to do computed properties on a type, right? So we could have stored area as a separate number within the rect struct. The problem with that is now we lose kind of a single source of truth when it comes to the area, right? If we store the area as, say, 50 and the width and height as 5 and 10, but then we update the height and forget to update the area, right? Now we have a bug in our code. So this is a great way to kind of have a one-line accessor to get the area of a rectangle, but we don't have to actually store that area in our struct as kind of duplicate data. So let's get down to the assignment. It says, let's clean up Textio's authentication logic. We store our user's authentication data inside an authentication info struct. Okay, so that's here. It's got a username and a password. We need a method that can take that data and return a basic authorization string. The format of the string should be authorization basic username : password, right? So this is the kind of standard basic authorization that's used in HTTP requests. The assignment says, create a method on authentication info called getBasicAuth that returns the formatted string. Okay, cool. So let's create a new method. And we can kind of reference this syntax over here. So it's func, and we want the receiver to be an authentication info struct. So I'll just call it AI. Ooh, that's actually confusing. Let's do auth_i, authentication info. And we wanted the name of the method to be called getBasicAuth. And it returns a string. Okay. And then we want to return this format here. So if you remember, we can use the format package to do that. So we'll return fmt.sprintf. Remember, sprintf returns the string rather than printing it to standard out or to the console. And we'll use that template. Username and password are both just strings, so we'll use %s for our formatting verbs. And then we can do auth I dot username first and auth I dot password next. Okay, cool. That looks correct to me. Let's run it. Perfect. Let's talk about interfaces. So an interface in Go is just a collection of method signatures. For example, take a look at this shape interface. So we have an interface, it's named shape, and it specifies two different method signatures. So area is a method that takes no parameters and returns a float64. Perimeter is another method that takes no parameters and returns a float64. Now, any type that implements both of these methods and matches their method signatures will implement the shape interface, which really just means that we can think of it and treat it as a shape. So for example, let's take a look at this rectangle struct. So a rect has a width and a height, both of which are float64s. And again, this is just a kind of standard struct. And it has two methods on it. One is the area method that takes no parameters, returns a float64. One is the perimeter that takes no parameters and returns a float64. And because a rectangle implements both of these methods, we can think of a rectangle as a shape. A shape is just anything where we can kind of calculate its area and calculate its perimeter. And multiple types can implement the same interface. So for example, this circle struct, it has different underlying data, right? Rather than a width and a height, we can represent a circle with just a radius. But to calculate its area and its perimeter, the calculation is a little bit different, right? We're using pi, for example. But the method signature is identical, right? We don't pass anything in because we have all the data we need on the circle struct, and we just return a float64. So both circles and rectangles, because they implement the required methods, can be thought of as shapes. Or we could say they implement the shape interface. Let's get into the assignment. I think it'll all start to make a little more sense. So the assignment says the birthday message and sending report structs have already implemented the get message method. So let's take a look at that. So birthday message is this struct here. Sending report is this struct here. They both have this get message method that returns a string. And they're just, it looks like the strings that they return are just a little bit different, right? The birthday messages get message function returns this like, hi, blank, it is your birthday on blank. And a sending report says your blank report is ready, right? So they're just formatted a little differently. Okay, so assignment says first add the get message method as a requirement on the method interface. Okay, so we need to finish the message interface and add a get message method that returns a string. Okay, cool. So now this message interface, because birthday message and sending report both implement this method, we can think of both of those as messages. Next, it says complete the send message function. It should print a message's message, which it obtains through the interface method. Okay, cool. So a message is an interface. So inside of the send message function, we don't actually know if we're dealing with, say, a birthday message or a sending report. We just know that we have access to a message. So really the only thing we can do with it is call get message, which we know will return a string. And it says it should print a message. So we'll do fmt.println. We'll just print out the message. Cool. Okay, now this is powerful. Right? Let's go take a look at how this code is actually called. So we have this test function that also just takes a message, and it sends that message, right? It's just calling our send message function here. But down here, and this is where it's most interesting, the test function is not past like interface literals. That's not even like a real thing, right? An interface is like abstract type that represents other types. Instead, because the test function takes an interface, we can pass into it any struct that implements that interface. So, for example, here on line 42, we're passing in a sending report. And then on line 46, we're passing in a birthday message. Those are two different types in a strongly typed language being passed in as the first parameter to a single function. But the reason it works is because we're using interfaces. Okay, let's go ahead and run this, see what happens. Your first report is ready. You've sent 10 messages. Hi, John Doe, it is your birthday. This looks great. This looks great to me. In Go, interfaces are implemented implicitly. And what that means is when we have a type, like in our last example, we had the rectangle type that implemented the shape interface, we never had to explicitly write anywhere on the rectangle struct that it was intended to implement the shape interface. Because it satisfied all the requirements of the shape interface, it just kind of automatically implemented it. And that's fairly unique to Go. In a language like Java, we might have to write something like this. We could take a look at this little example here. We've got this employee interface and a contractor struct. If we wanted the contractor to implement the employee, we would need it to still fulfill the interface, right, by implementing all the methods, but we might need to also explicitly type something like implements employee, right? We'd explicitly say that we intend to implement that interface. In Go, it's done automatically. Let's hop into the assignment. It says, at Textio, we have full-time employees and contract employees. We've been tasked with making a more general employee interface so that dealing with different employee types is a little simpler. Add the missing getSalary method to the contractor type so that it fulfills the employee interface. Okay, cool. So we have the employee interface, we have the contractor struct, and if we look at the full-time struct, it looks like it already implements the employee interface. So we just need to add the missing method because right now a contractor has a getName but does not have a getSalary. Okay, cool. So let's go ahead and do that. We'll do employee getSalary. It returns an int. And a contractor's salary is their hourly pay multiplied by how many hours they work per year. Okay, so be something like C dot hourly pay multiplied by C dot hours per year. Okay. And just because I'm curious, I want to go look at how a full-time salary employee works. Yeah, so you can see the way that a full-time employee, their salary is calculated is totally different. Like their salary is actually just stored, probably because the way we think of full-time employees is like, you know, you make $60,000 a year, you make $70,000 a year, whereas contractors often get paid by the hour. So it makes sense that they have a different calculation. And then down here in the test suite, this looks very similar to the last assignment where the test function is able to take as inputs any type of employee, right? So we can pass in both full-time and contractors here. Let's go ahead and run that. Jack, Bob, and Jill, we can see all of their salaries, even though Jack is full-time and Bob and Jill are both contractors. So that looks good to me. In Go, types implement interfaces implicitly because it kind of decouples the definition of the interface from the definition of the type. The type doesn't even really need to know that it implements a certain interface. And that's really, really cool because it means it's easy for a type to implement lots of different interfaces. So the quiz question here is, how is an interface fulfilled? Answers are, a type has all the required interfaces methods defined on it, or a struct embeds the interface in its definition. And the answer is going to be, it has all the methods defined. The next question is, can a type fulfill multiple interfaces or implement multiple interfaces? And yes, why not? Another quiz question. Go uses the blank keyword to show that a type implements an interface. And the answers are fulfills, implements, inherits, and there is no keyword in Go. And the answer is that there is no keyword in Go. Interfaces are implemented implicitly. In the next question, it says, in the example given, the blank type implements the blank interface. Let's take a look. So example here, we've got the shape interface, circle struct, circle has an area method. So it looks like the circle type implements the shape interface. Like we talked about before, a type can implement multiple interfaces. It just needs to have all the methods for all of the different interfaces. For example, the empty interface, so that's this definition right here, this is an interface with no methods required, is actually always implemented by every single type in the Go programming language. Now, it's often not a very useful interface because you can't really do anything with an empty interface. You have no methods to call. Let's jump down into the assignment. It says add the required method so that the email type implements both the expense and printer interfaces. Okay, cool. So we've got these expense and printer interfaces, two different methods we need to implement. And we have this email type with an isSubscribed Boolean and body string. Cool. All right, cost method. If the email is not subscribed, so if not e.isSubscribed, I believe is what the field was, then the cost is 0.05 times the length for each character in the body. So the length e.body. Now, remember, Go is strongly typed, and we can't multiply an int by a float directly, so we need to cast this integer. Sorry, I think I highlighted those backwards. The length of the body is an integer. This is a float. So we need to cast the length of the body to a float. So we can multiply a float by a float. Otherwise, we'll return it's 0.01 times that same thing, the length of the body. Cool. The print function should just print to standard out the email's body text. Easy enough. fmt.println e.body. Okay. So now our email struct implements both of these interfaces. And if we come down here to look at the test function, this is interesting. The test function takes an expense and a printer, right? So we can use both of those methods there. And actually, the email struct, so we're creating instances of emails here, we're actually passing it into test as both the expense and the printer, right? Because it makes sense. It implements both. Cool. Let me run that. Oh, what did I screw up? 0.05 times float64 length. Value of type float64 is not used. Let's see. 0.05 times float64 length of e.body. What did I screw up? Value of type float64 is not used. Oh, I forgot my return. Cool. Let's try that again. Okay. So, printing with cost 11 cents. Hello there. Printing with cost $1. I want my money back. Yeah, that looks pretty good. Let's submit it. Up until this point, we haven't really been naming the arguments of our interface's method signatures, but we totally could. So if we take a look at this, this is the copier interface. It's a copy method that it requires, which takes two strings and returns an int. The interesting thing is when you look at this method signature, it's kind of hard to tell what the intention behind the interface is. It's like, great, it takes two strings, but what are those strings supposed to represent, right? So here, we can take a look at what I would consider a better interface definition, where the copier interface actually has a copy method that specifies the source file is kind of the name of the first parameter, and the destination file is the name of the second parameter, and then bytes copied is the integer that's returned. So, you know, the functionality here is identical, but now we have much better, I mean, I would consider it documentation of what the intention behind this interface is. So the question is, are you required to name the arguments of an interface in order for your code to compile properly? No, it'll work fine either way. Next question is, why would you name your interface's methods parameters, right? Like, we don't need to. Why would we do it? Execution speed, memory savings, or readability and clarity. It's going to be for readability and clarity. Type assertions. So type assertions are something you'll see every once in a while. I would argue they're probably not super common, but you will come across them. And the whole purpose of a type assertion is so that you can take an interface and kind of cast it back into its underlying type. So in this code sample here, we can kind of assume that S is an instance of a shape interface. And at this point in the code, because it's just an interface, we don't know necessarily if it's a circle or maybe a square or maybe some other type. So what we do is we do a type assertion to cast it to the circle struct. And basically what happens here is on the left-hand side of the this short declaration operator here, we get back the instance of the circle. So this is going to be an instance of the circle struct, again, the underlying struct behind the shape interface. If it was a circle, right? Because we can't be sure. If we had a shape, we're not sure if it was a circle or maybe something else. But this OK variable, this is going to be a Boolean. And if it's true, then it was a circle and we should have a valid kind of filled out circle struct. If OK is false, then we kind of have to discard the circle because we weren't able to parse out the shape as a circle because it wasn't a circle. So let's move on to the assignment. If it's an email, then it should return the email's to address and the cost of the email. If the expense is an SMS, then it should return the SMS's phone number and cost. If the expense is any other underlying type, just return an empty string and a 0.0 for the cost. Okay, cool. So we've got this get expense report. It takes an expense as input, and my guess is, yep, expense is this interface. So our job is to kind of try to cast it into the potential underlying types email and SMS. So first we do email, okay, expense dot, and we'll cast it to an email type. If okay. So if it's an email, return the email's to address. So it's going to be return email dot to address as that string there, and also its cost. So email dot, looks like cost is a method. Email dot cost. Okay. Next we can do s okay. E dot cast to an SMS. So if it's an SMS, we can return SMS's to phone number, and the SMS dot cost. I believe that's also just, yep, just a method. Okay, and it says otherwise, if it has a different underlying type, return empty string and 0.0 for the cost. Okay, cool. That feels at least like we followed the instructions. Let's see what we get. Not enough arguments in call to SMS.cost. Let's take a look at SMS.cost. Have, want. What did I screw up here? Should be s.cost. I named the struct s. All right, let's try that again. Report the email going to John Doe will cost 11. Email, the SMS. Okay, cool. And invalid expense. Perfect. That feels right. I can come down here and check the test suite. Yeah, invalid. Okay, cool. Let's submit that. When we want to do a lot of successive type assertions in a row, there's actually a better way, and that's with type switches. So here's a syntax for a type switch. Basically, we have an interface, and we cast it at the very top of the switch, and then we can actually check and kind of pattern match against different possible types. If none of the types that we've specified are the matching underlying type, then it will kind of fall down to the default case. So let's write some code and see how it works. Down in the assignment, it says, after submitting our last snippet of code for review, a more experienced gopher, or term for a Go developer, told us to use a type switch instead of successive assertions. Let's make that improvement. Implement the get expense report function using a type switch. Okay, cool. So kind of the same thing though. If it's an email, we'll return a to address and a cost. If it's an SMS, then we should return a phone number and a cost, blah, 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 right? The difference is we're going to use a different syntax this time. Okay, so we're going to be using this switch syntax. So switch value : e dot type. Okay, open brackets, case. We're interested in if the expense is an email. So case email. Now the interesting thing is within this case block, V is an email. So I can treat it like an email. So I can do return V dot, oh, what was it? To address, I think. Yeah. To address V dot cost. Case SMS. Return V dot to phone number, I think it was. To phone number. V dot cost. And default. Return. I think it was empty string, just 0 values, right? Empty string and 0.0. Okay, cool. Let's see what happens with that. Oh, am I forgetting? Nope, I've got... Oh, I'm indenting a little weird. There we go. Let's run that. Cool. The SMS is going to this number with this cost. Got some emails and costs. Okay, that's looking good to me. Now that we've learned what interfaces are and how we use them, let's talk about how we can use them more effective and in a sort of idiomatic and clean way. If you forget all of the other advice that we're going to go over when it comes to writing clean interfaces, don't forget this one, and that is to keep interfaces as small as you can. The best, the cleanest, and the most useful interfaces typically just have 1 or 2 methods defined on them. Imagine a simple stringer interface. It has one method defined on it called string that simply returns a string. You can take that interface and implement it on basically any type, and now you have a super useful interface for logging out string representations of different types. There isn't a hard and fast rule about exactly how many methods you should be defining on your interfaces, but what you really should be doing is looking for kind of the minimal behavior necessary to accurately represent an idea or concept, right? So for example, here's a slightly larger interface from the standard library. Again, normally we'll see interfaces in the standard library with maybe just 1 or 2 or 3 methods. This one has 5, but this is kind of still the minimum amount or the minimal necessary behavior that we need to describe a file, like a file in your file system, right? We need a way to close the file. We need a way to read it. We need a way to seek to individual kind of sections of the file. So this is an example of a slightly larger interface, right? I would say 5 methods is definitely on the larger end, but it's still a good interface because it's using as little behavior as it possibly can to describe an operating system file. So the question that goes along with this is, interfaces should have as blank methods as possible, and the answers are complex, few, and many, and the answer is going to be few. The next mistake that I've seen new Go developers make is when they write an interface that sort of knows about the types that they've intended to satisfy it. So for example, if you have a car interface and you've defined an isFireTruck method on the car interface that returns a bool, whether or not it's a fire truck, that's probably a mistake. You would actually just want to use a type assertion or a type switch if you really needed to figure out the underlying type. You should not make your interfaces aware of the underlying types. This also breaks rule number 1, right? Because rule number 1, we don't need to know if a car is a fire truck for like the minimal behavior of a car. I mean, you can see how this sort of design pattern would get out of hand very quickly because we might need to also define other Booleans like is pickup, is sedan, is tank, right? If you start catering to all of the underlying types of a given interface, your interface is going to be really bloated and become very, very large. So the question here is actually the reverse. It says it's okay for types to be aware of the interfaces that they satisfy. If it were flipped around, the answer would definitely be false. But because we're talking about the types being aware of the interfaces they satisfy, I don't think that's necessarily a problem. They don't need to be aware of them, right? Because again, in Go, interfaces are satisfied implicitly. But I would argue to some extent they are aware of them because the developer had to go, in some cases, out of their way to satisfy the implementation of an interface. So I'm going to go with true on this one. So now this is the reverse question. It says it's okay for interfaces to be aware of the types that satisfy them. No, they should not be aware. Finally, I just want to talk about how interfaces are not classes. Sometimes this can get mixed up, especially if you're coming from an object-oriented background. Interfaces are just a very different idea. Interfaces are not classes, they are much slimmer. Right? Classes have a lot of functionality going on. Inheritance is a fairly complex topic. Interfaces are honestly just a simpler idea. Interfaces don't have constructors or deconstructors that require that data is created or destroyed, right? So that's another way that they differ from classes that have kind of this inherent setup and tear down situation. Interfaces are not hierarchical, right? There's no hierarchical inheritance tree when it comes to interfaces. And the most interesting one is that interfaces define function signatures, but not underlying behavior, right? So this is actually a big difference between interfaces and classes. In a class, a child class can inherit behavior from a parent class, which can kind of dry up your code, right? Don't repeat yourself. In Go, that's not the case at all. An interface doesn't dry up your code. You still have to go implement all of the methods on all of the different types individually. Interfaces just allow us to use all of those types kind of in the same places. Later in this course, we'll get to talk about generics, which is a way to kind of dry up your code and, funny enough, kind of uses interfaces under the hood or kind of as a part of the generics system to make that happen. So finally, the question is, interfaces allow you to define a method's behavior once and use it for many different types. That's false. Go has a very unique way of handling errors. Really quickly, let's review how JavaScript handles errors. And the way JavaScript handles errors is very similar to Python or Java. It uses a try-catch paradigm. And let's contrast that with how Go handles errors in its sort of unique way. Let's pretend that we have a function called getUser. And we'll start with JavaScript. So we have a function called getUser. Whoa. And it returns a user. So we'll do const user equals getUser. And we have to wrap the getUser function, the call to the getUser function, in a try block because we know that the getUser function can throw because let's just say, for example, maybe the user doesn't exist. Okay, cool. So if something goes wrong, we add a catch block, and if this function throws, execution will stop. We'll enter the catch block and do whatever's in here. For now, we can just console.log the error. Now let's take a look at what this function looks like in Go. We do something like this. We do user error equals get user. If error does not equal nil, then we could print out the error and return so that we don't continue. And then down here we could, deal with the user object. So use user here. And for consistency's sake, we could say use user here after the user object is created in JavaScript. Okay, so what's the difference? Well, let's talk about the first reason why I prefer Go's error handling to JavaScript's error handling. Let's pretend we need to go get some data for the user after we've already kind of retrieved the user successfully. So let's say we need to go get the user's profile picture. Well, in Go, all we would do is call the next dangerous function. Let's say get user profile, and maybe it takes a user.id as input, right? So we need to successfully wait for the user to come back, and then we can go fetch its profile. All right, so this looks very similar. We're doing another dangerous function, get user profile, and it returns a profile and an error. If an error with the profile occurs, again, we'll just kind of print out the error and return. Otherwise, now we have a profile object. Okay, what would we do in JavaScript? Well, in JavaScript, we can't just take this try-catch and paste it down here and update some stuff. This will not work. If we do get user profile, user.id profile. The problem with this code is that user is only available within this try block. It's scoped to the try block. Right? So this user object here will be undefined. So the normal thing to do in JavaScript would just be to take this line here and inject it within the try block, the original try block. right? So now I'm doing my second dangerous function after I do my first dangerous function. The reason I don't like this is that the logic for handling the errors is now all in one place. If I want to handle the error for the getUserProfile function differently or separately, then I want to handle the error from the getUser function, I have to actually nest the whole try catch like this, right? So now user.id is accessible because I'm in the same try block, but I get a second catch block. So we kind of get this nasty nesting if we want to treat each individual error separately. And this kind of brings us to the second reason why I prefer Go's error handling, and it's that it forces us to think about each individual error that's passed back from a dangerous function. So again, in JavaScript, kind of the normal thing to do, unless you really needed separate error handling, would be to just kind of do all of your dangerous stuff in one large try block. The problem with this, in my opinion, is that it doesn't encourage me to remember which of these functions is dangerous in the first place. For example, maybe this is a safe function and this is a dangerous function that can potentially throw an error, but looking at this code from kind of a calling perspective, I don't really know that that's the case. Whereas in Go, because a function returns kind of the valid data and the error with every function call, I know for a fact that the getUserProfile function can throw an error because it returns an error value. This will probably make more sense if I actually write out some of these functions. So in JavaScript, the getUser function might look just like this. Function getUser. We could say do some getUser logic here. And then maybe it returns, a user. Looking at the function signature, all I can tell in JavaScript is that this function takes no arguments. And the only way for me to know what it returns is to go find that return statement and see, oh, okay, it returns a user. However, in Go, I actually get two super helpful things in the function signature. And remember, the function signature is just kind of that first line of a function definition. So in Go, if I were to write the function definition for the getUser function, it would be something like this. Func getUser doesn't take any inputs, but it returns let's say a user struct and an error, right? And then we have some kind of do getUser logic here, right? So now, just by looking at this function signature, I can tell that it returns a user and that it could possibly return an error as well that I need to go handle. Whereas again, in JavaScript, not only do I not get to see in the function signature what is potentially returned, but I also don't know that this function can throw. I have to kind of go digging deeper into the function definition to see if there's potentially something dangerous going on in the meat of the function. So again, to reiterate, because this is actually a super important point when you're learning about how errors are handled in Go, the primary reason I like error handling in Go is that it forces me, as I write my code, to be kind of hyper aware of every potential error and make sure that I write code that handles it. So now that we understand what error handling in Go kind of looks like from a high level, let's dive into the details. Errors in Go are just values, and specifically, they're just interfaces. So the built-in error interface is an interface with a single method, the error method, and that method returns a string describing what went wrong. So how do we actually go about handling errors in code? Well, let's take a look at this function right here. So this is a function in the standard library. It's called ASCII to integer. It takes a string and attempts to convert it into an integer value. And potentially that can be problematic, right? Because you can write strings that aren't numbers under the hood. Okay, cool. So what do? We get back an integer and an error. And in essence, it's really simple. The error is either nil or it's not nil. If it is nil, that means everything went fine and nothing went wrong. So if the error is nil, it means there is no kind of string representing what went wrong because nothing went wrong. However, if the error is not nil, that means something did go wrong, right? So if the error is not nil in this case, then we'll print an error message and return from the function, right? So we're basically writing guard clauses that say something went wrong, let's handle this error and get out of here, right? Enough talk, let's write some code so you can see what I mean. Let me expand this so it's a little easier to see the code. Okay, the assignment says, we offer a product that allows businesses that use Textio to send pairs of messages to couples. It's mostly used by flower shops and movie theaters. Okay, great. Complete the send SMS to couple function. So that's this function here. It should send 2 messages, first to the customer and then to the customer's spouse. So use send SMS to send the message to customer. If an error is encountered, return 0.0 and the error. Do the same for message to spouse. If both messages are sent successfully, return the total cost of the messages added together. Okay, I think I understand what's going on. So we're basically going to send both of these messages one after the other. If any errors happen, we kind of abort early and return the error. Okay, so send SMS takes a message as input. So first we'll say send SMS, and we'll send the message to the customer. And send SMS returns a float64 and error. So we'll say, I think it's the cost. Return the total cost. Okay, yeah. So cost, error, send SMS. All right. If error does not equal nil, so if there was a problem sending the SMS, return 0.0 and the error. So return 0.0. Right? Because this function send SMS to couple returns the total cost and an error. So we're saying if we failed to send the SMS, then it costs nothing and we'll return the error that describes what went wrong. Otherwise, we'll do it for the message to spouse. So we kind of are just going to do this exact same thing. So I'm going to say cost for let's say customer, cost for spouse, and we'll be sending the message to the spouse. Cool. All right, now if we get to the bottom of the function, that means nothing went wrong. So we can return cost for customer plus cost for spouse and nil, right? Because if we get down here, nothing went wrong, so we don't have an error to return. Okay, let's go ahead and run this code and see what we get. And I want to just scroll down and take a look at some of these test cases. Okay, message for customer. Thanks for coming into our flower shop. Message for spouse. We hope you enjoyed your gift. Error. Can't send texts over 25 characters. Okay, cool. So, I mean, if we look at the send SMS function, it actually throws an error, or I shouldn't say throws because we don't throw in Go, right? But returns an error value that says can't send texts over blank characters. So that looks correct to me. Here we've got message to customer, message to spouse, total cost. Okay, this is looking pretty good to me. I'm going to go ahead and submit that. We talked about how error handling in Go is all built around the error interface. In fact, let's just review that really quickly. This error interface is really just an interface that wraps a method returning a string. Because if you think about it, at the end of the day, an error is just a kind of nullable string. Either it's a string representing what went wrong or saying what went wrong, or it's nothing because nothing went wrong. So being good at handling errors in Go has a lot to do with being good at formatting strings or formatting useful error messages. So let's review how we format strings in Go. Most formatting Go is built around kind of these formatting verbs that are defined in the format package, the FMT package of the standard library. So for example, the sprintf function returns a string where it interpolates the values passed into the function after the formatting string into the formatting string where the verbs exist. So for example, this first %v is replaced with name. The second %v is replaced with age. %v is the verb we use for sort of the default format, right? If you format an integer using %v, then it kind of just prints the integer in string form. But there are other ways that we can format stuff. For example, the %f verb is used to format floats. And you can actually specify how many decimal places you want to show up in your output string by kind of prefixing the f portion with a 0.2 for 2 decimal places, or say a 0.1 for a single decimal place. So let's jump right into the coding assignment. Assignment says we need better error logs for our backend developers to help them debug their code. complete the get SMS error string functions. That's this one right here. It should return a string with this format. Okay, cool. So I'm just going to jump right ahead. So it should return fmt.sprintf, right? Because we're trying to format a string. This format. Let me expand that a little bit. Okay, so return a string with that format. Cost is the cost of the SMS, so I'm going to replace cost here with the cost formatted to 2 decimal places. So %.2f, right, for 2 decimal places. And replace recipient with the stringified representation of the recipient's phone number, which is this string here. So %v. It's important to point out, I could also use s here to format a string, but v and s do the same thing effectively when you're working with strings. And then we need to pass in as parameters the values that we want to format or that we want to interpolate into the string. So it's going to be cost and recipient. I'm going to dedent that because that is some crazy formatting. Okay, that looks better. All right, SMS that costs %.2f to be sent to %v. This looks good to me. All right, I'm going to go ahead and run that and see what we get. Ah, right, can't forget to import the formatting package. Let's run that. Okay, SMS that costs 1.40 to be sent to this string cannot be sent. Awesome. This looks correct to me. I'm going to go ahead and submit that. Let's talk about building our own custom error types. So remember, the error interface is an interface. In fact, let me jump back and show you what it looks like again. So it's just this interface here. And because it's an interface, that means we can build our own types, like this user error struct here, that implement that interface, which means they can be used as errors. And remember that the error interface just has one single method that we need to define, right? The error method that returns a string. And as long as we have that, then our type can be used as an error. So for example, we could create this user error type that stores a name, and then we can use it as an error to format an error message that contains the name of the user's account who had an error. So for example, in this snippet here, we have a send SMS function. And if we're not able to send a message to a user, we can actually just return that user error struct with the user's name. And again, that is an error. We can return that struct as an error type because it implements the error interface. The caller of this function would then just treat it like any other error. The reason this is useful is that we can store structured data within our errors. So if we want to format them a specific way, we have access to sort of dynamic data like a name. Let's write some code that uses this concept. So the assignment says, our users are frequently trying to run custom analytics queries on their message deliverability metrics, right? So we're sending lots of messages. We want to know, are these messages getting delivered? They end up writing a bad query that tries to divide a number by 0. It's become such a problem that we think it would be best to make a specific type of error for dividing by 0. Update the code so that the divide error type, so that's this error type here, or rather this struct here, implements the error interface. Its error method should return a string formatted in the following way: cannot divide dividend by 0. Okay, let's write that method. So it's going to be a function on the divide error type. So I'm going to name it DE, which is a divide error. And the name of the function must be error, takes no arguments, and returns a string. Right? So that's the function signature we need to use to implement the error interface. And then we're going to return a string, and we're going to need to format the string. So we'll use sprintf. The format package is already imported. And this is our template. And dividend, in this case, is a float64. And it says here, dividend is the actual dividend. Use the %v verb. So %v, okay. So we're just going to kind of do the default formatting for a float64. And let me indent all this so that it's kind of readable. Where dividend is the actual dividend of the divide error. Okay, so we'll do de dot dividend. That will interpolate there. Okay, that looks correct to me. I think we've implemented the error interface properly. Let's go ahead and run that. Uh-oh, I forgot my comma. This is kind of an interesting quirk of the Go programming language. If you add a new line after the last parameter to a function, you have to put a comma. So this would work, all right? And this would work, but this does not work, right? That's what I did the first time. So just kind of something to watch out for. Okay, so let's take a look at this. Dividing 10 by 0, cannot divide 10 by 0. Dividing 10 by 2, quotient 5. Dividing 15 by 30, 5. Quotient. Okay, this is looking like it formatted properly. Let's submit that. So we've got a quiz question. It says, what is the underlying type of an error? Is it an interface? Is it a struct? Is it a string? Well, it could technically be a struct or a string, right? Like we saw in the last assignment, but the most correct thing would be to say an interface, because it must always be an interface, right? It must always implement the error interface. It could also be a struct or a string, but it will always be an interface. Next question is, can a type be an error and also fulfill another interface? Well, errors are just interfaces, and we know that types can fulfill any number of interfaces as long as they have all of the required methods. So yeah, there's no problem with this. Let's talk about the errors package. So the standard library in Go has an errors package that exposes a few useful functionalities, but the one we're most interested in right now is the errors.new function. So the useful thing about the errors.new function is it allows us to create a new error from just a string. So we don't need to kind of, define a new struct or a new type and then have it explicitly implement the error interface. That can be a lot of code if all we want to do is kind of return an error with a very specific string. Let's go ahead and use it. The assignment says, Twilio's software architects may have overcomplicated the requirements from the last coding assignment. Yeah. All we needed was a new generic error message that returns the string no dividing by 0 when a user attempts to get us to perform the taboo, right? The taboo of dividing something by 0. Complete the divide function, use the errors.new function to create an error when y equals 0 that reads no dividing by 0. Okay, so this is pretty straightforward. Basically, if y is 0, which means that the number that we divide by would be 0, which is obviously a huge problem in mathematics. You're not allowed to do that in Go or most programming languages that I'm aware of. So we need to return an error here so that this operation never happens. So we'll return errors.new. Looks like the errors package is already imported for us, and we just need to return an error that says no dividing by 0. Okay, let's go ahead and run that and see what we get. Oh, I screwed up. This function returns a float64 and an error, so we should return a 0 value for that first value when we're returning a non-nil error. Let's go ahead and run that. Cool. Dividing 10 by 0, no dividing by 0. All of this looks good to me. Let's talk about loops in Go. So if you are familiar with loops in other languages, loops in Go syntactically are very similar to, say, loops in JavaScript. The main difference is just that we don't use the parentheses around kind of the signature of the for loop, which again is very similar to how if statements in Go work. We're basically just dropping those parentheses syntactically. The initial portion runs at the beginning. So for example, in this snippet of code where we're looping over the integers 0 through 9, in the initial section, we're just initializing a variable I and setting it equal to 0. In the condition section, we're checking and making sure that I is less than 10. So at the end of every kind of iteration of the body, which in this case, we're just printing I in the body, we're going to check and make sure that I is less than 10. If it is, we'll continue on to the next iteration of the loop. Otherwise, we'll be done. And then at the end of every iteration, we'll also be running this after section. So we'll be incrementing I. And that happens before the condition is run. So for example, if we increment I to 10 and then I is no longer less than 10, we will not continue on to the next iteration of loop, which is why this prints 0 through 9 and not 0 through 10. Let's jump right into the assignment. It says, at Textio, we have a dynamic formula for determining how much a batch of bulk messages costs to send. So we need to complete the bulk send function. It takes a number of messages as input and returns a float64, which it looks like will be the total cost of the batch of messages. Okay, each message costs 1.0 plus an additional fee. The fee structure is, so it's going to be, first message is 1.0 plus 0, so 0 is the fee. Second message is 1.0 plus 0.01. Third message is 1.0 plus 0.02. Okay, cool. And then our job is to use a loop to calculate the total cost of all of these messages for, the number of messages that we've been given. Okay, let's just start writing some code. So total cost, I'm going to just start it out at 0.0, and then we'll use a loop for I colon equals 0 to do like num messages iterations. So, a number of iterations equal to num messages. So start I at 0. And then we'll do I is less than num messages and I plus plus. Okay, so this kind of body of the for loop should execute num messages times. And we're going to want to add to the total cost, so plus equals, and we're going to use this formula. So it's going to be 1.0 plus this fee. And how do we calculate that fee? Well, it looks to me like it is 0.01 times basically the message number, right? So for the first message at index 0, I equals 0, it's going to be a fee of 0. So if we just use I, this should work, because if I is 0 and we multiply that by 0.01, anything multiplied by 0 is 0, right? So we'd get 1.0 plus 0. For the second message, I should be 1. So